Alright, example 3. Notice here that we're going to start getting into some curves. So we're looking at the curve y equals x squared. Luckily I have a curve type drawing tool. And let's go ahead and get ourselves set up here. So if we're trying to get this curve going, we're looking at this bounded region. It's bounded by the x-axis, or the equation y equals 0, the equation x equals 2, and the curve y equals x squared. The first thing that we're going to be rotating around is around the x-axis. So we need to ask ourselves, are we attached? Yes, we are attached. So all we need is big R. And I know that we're going in the x direction. And I know that these boundaries are determined by the boundaries for my original equation. So we start at 0, that's where it hits the x-axis, but it also comes down on this line x equals 2. Just for fun, because we're going to be seeing it later, if we're at 2 on the x-axis, that means we're at 4 on the y-axis. So we're going from 0 to 2, we just need to define that radius, that large radius. Well, how far is it for this large radius? It's from that curve edge down to the x-axis, so r is going to be x squared minus that axis of rotation is 0, so it's just x squared. We don't need the little r, so we have big R equals x squared. So our volume is going to be pi times the integral from 0 to 2 of x squared squared. Why? Because it's r squared, and r is x squared, but this is r squared squared. If I needed to simplify that, I could just say it's pi times the integral from 0 to 2 of x to the 4th dx. Let's keep working our way through. Part B here, we're going to rotate around the line y equals 4. Let's get our picture set up so we know what we're looking at exactly. Now we have this curve. And we're coming down this line x equals 3 again. Color in this space, this is what we're looking at. But the difference now is we're rotating around the line y equals 4, around this line here. So we have to ask ourselves, are we attached? No, we're not. We have all this empty space that we got to somehow get rid of. So we got two radiuses to think about. We're going to have the volume equals the integral from, we still have the dx direction because we're moving from left to right here, from 0 to 2, from x equals 0 to x equals 2. And now we got to figure out our big R squared minus our little r squared, and we got to remember the constant pi on the outside. So let's start with big R squared. Big R is going to be from the axis of rotation all the way to this outer edge. And in this case, that's constant because that outer edge is parallel to the axis of rotation. That is going to be 4. Little r is going to be on the inside here. It's going to be from the axis of rotation down to the curve. So that distance is going to be 4 minus x squared, top minus bottom there. So we got 4 minus x squared for little r. Big R is 4. So the volume is going to be pi times the integral from 0 to 2 of 4 squared minus, and then we got the whole quantity, 4 minus x squared dx. Remember, right now, again, we're mostly focused on setting these up. These can always go back and do the antiderivatives to evaluate them. So we're still working our way through. Now we're going to rotate around the line y equals 5. Still have the same curve. Y equals x squared. And you know what? Let's go ahead and make that a little bit shorter. Because now that we're rotating around the line y equals 5, we're more up here for our rotation. rotating around this line, y equals 5. Again, we still have the same bounded region, but now we have a lot of empty space, not just a little. We got all this here. We went up, we added another couple of units above it. So when we look at what we're trying to find, we ask ourselves, are we attached to our axis of rotation? The answer is no. So we know that our volume is going to be pi times the difference of the radii each squared. We know that we're moving horizontally because we have vertical disks, so we're going to have dx. We still have x equals 0 to x equals 2 for our limits. So we just got to define that big radius and little radius. So looking at the big radius is from the axis of rotation to the outer edge of that boundary. So that is 5. This is kind of similar to the last one. The inner radius is also similar in that it goes from that axis down to just the curve. It stops at the curve. So because it stops at the curve, we do 5 minus x squared. So this one we have 5 minus x squared for little r. Our big R is 5. So to set up our actual volume, putting in the pieces that we have, it's going to be equal to pi times the integral from 0 to 2 of 5 squared minus, and we got 5 minus x squared quantity squared dx. Let's check out part D, the y-axis. Now for D, E, and F, we're actually going to be going in the perpendicular direction. So first, start with our curve. And we have this bounded region, again in the blue. But now as we're rotating around the y-axis, we're going to have a lot of empty orange space in here too. Couple things to remember. We went from 0 to 2 in the x direction, but earlier we had mentioned that we go up to y equals 4 because this line right here is y equals x squared. So that tells me I do have empty space. That means I have volume equals pi times big R squared minus little r squared. Now and I'm figuring out my direction. Since my disks are horizontal, that means I'm going to be moving in the vertical direction. So I'm going to have dy. That means that these boundaries are also in terms of y. I'm going to be going from 0 to 4. So I just need to define what that big radius and little radius is. The big radius is from the axis of rotation to the outer edge, which in this case is constant. It's just 2. The inside radius is going to be out to that curve. So I need to figure out what that curve is, but I need to figure it out in terms of y. I know that y equals x squared, so if I were to change that into terms of y, it's some function of y. It's going to be x equals square root of y. So little r is just square root of y. So we have square root of y for our little r, and big R is going to be 2. If we put all this together, using the same information we've been doing, we got pi times the integral from 0 to 4, and 2 squared minus square root of y squared, dy. A couple more and we're done with this. The line x equals 2. Okay, so let's see what we have here. We've still got a horizontal vertical axis. We have our curve. And we know that we kind of hit here at y equals 4. And this comes down at x equals 2. So that's going to be interesting because now we're rotating around, and it almost seems like it'd be harder, but I think it's going to be easier. I'll let you know why in a second. Because when we get to our first question, is it attached? It is attached. It's attached to the axis here. So when I try to find the volume, I only need to find the big radius. And I know that I'm still going from 0 to 4 in the y direction. I just need to figure out what this big radius is. Well, it's always going to be top minus bottom, or the bigger number minus the smaller number. In this case, 2 on the x-axis winds up being bigger than square root of y. So it's going to be big R equals 2 minus square root of y. It's from edge to edge. So the little r we don't care about. The big R is 2 minus square root of y. So as I put these two pieces together, I'm going to have volume equal to pi times the integral from 0 to 4 of 2 minus square root of y quantity squared dy. There we go. Last one, around the line x equals 4. So this is going to present a new challenge to us. We're going to have a little bit of empty space. So we still have that same curve. And now we have a line that we're spinning around a little bit further out. Actually about double the space out here. So we're going to be spinning around this line right there. On line x equals 4. We're still bounded by this line x equals 3. So we still have that same blue shaded area that we've been doing for the last few parts of this example. But now we have this empty space between the bounded region and the axis of rotation. So because we're not attached, we know that we're going to have the big R squared minus the little r squared. We know that we're still moving in the direction of y because our disks are horizontal. So we're still going from 0 to 4. We just got to define what that big R and little r is. Well, big R is from the outer edge all the way to the axis of rotation. So big R in this case is going to be, well, this goes all the way out to 4, so it's 4 minus square root of y. Now remember that this has to be in terms of y. Can't use x squared, y equals x squared, because we're not using x's, we're doing it in terms of y. And little r then is going to be this inside piece, which is constant the entire time. It goes from 4 down to 2. So little r is just 4 minus 2, which is really 2. So little r is 2, big R is going to be 4 minus the square root of y. When we set this up, we still have the constant pi. We're going from the integral from 0 to 4 of big R, which is 4 minus square root y, quantity squared, minus, and then we have 2 squared for that inside radius, dy. I know I went through these kind of fast, but just trying to show you the examples worked out in case you need to see them. Alright, next is example number 5, 3, 4, one of those. We'll see you there.